Hello. Hi Nipun. Hi Desin. Hi Quantum Developer. I need to put the chat into the... Hi Upe Krishna. Hi PA Minerva. I don't know if I'm pronouncing this correctly. Thank you. Okay, now the chat is visible. Okay, so the audio, everything is good? Is it like... Okay, nice. So okay, in the like, I want to briefly talk about what I want to do today. Basically, I mean, I'm not sure how far I will come, but I want to make something similar to this. If you have seen my first devlog episode, this is what I want to do. And for that, I want to use the... Wait, let me set up the Windows short. Yeah, I want to use the SDL GL template for this. And the first step, what I want to do is like go over the code of this SDL GL template and talk about what's happening here, and then extend it. So I set up a folder here so I can clone this. Can you, is the text readable? Like, is it big enough, or do you want me to increase the font size or something? Oh, okay. As I assume the yes is okay. Nice. Thank you. So, so the way this program here works is okay. Nice. Thank you. Ah, yes. Okay. Hello, Lord Richard. Yes, I can do that. I want to write a 3D renderer because in the stream series, I want to implement computer graphics papers in a live stream, or at least that's what I want to try. So, for example, um, some of one of my viewers brought me to this paper because he remembered some program that he wrote in university, I think, or some friend that wrote this program. And then I discovered this paper here, and uh, I mean, the renderer I used in my devlog was written by me still, but I mean, I just didn't want to just copy it because then you don't know how this renderer works, and that's why I thought maybe I could just write the renderer in a stream too. And it's nothing. I don't want to make a super complicated renderer. This is so. I hope it doesn't take a very long time to do that. So I just want to take 1 or 2 streams to write this renderer, so I can use the renderer for future streams as a basis for the paper implementations. Like for example, this paper here. Exactly, yeah, sandbox. And when we are finished with the renderer, we can like draw a model or something, and then we can implement some of the physics stuff here described. And that's basically the plan. And today I want to write a renderer and explain some of the maths. What do you mean, like loading the 3D models? I'm not sure. I didn't. So yeah, that's the other thing. I didn't want to write everything from scratch, because then it would take like very long. So instead, I want to use a library, for example, for the model loading, because that's not really part of a renderer. And I'm not sure yet. I thought maybe I can use tiny what's it called? Tiny OBJ. But I've never used this, so I don't know. Maybe you know some libraries to load models that's really good. I don't know. And the other thing is, I want to implement the math myself, but instead of writing everything from scratch, like I can show you. So this is the repository of my game of my devlog series. And you can see okay. You can see I basically had to create all these. It's a bunch of boilerplate code, like creating operators and like multiplying a matrix with a vector, or multiplying matrices, or transposing a matrix. So that's very much code. And this is why I thought maybe I can use the Eigen library. I don't know if you know the Eigen library. Just for the basis of the program. But I still like using this library, so I can use operator overloading, and the types are all there, but I still want to implement the math functions like rotation matrices or something like this myself. So it's interesting for you, maybe. I thought. Okay, I don't know FBX. I heard about ASM, but it seems like it's pretty. ASM is pretty huge, right? Oh, I forgot to. It may be the case that I need to work with matrices that are bigger than 4 by 4. So, for example, in this paper here, you need to invert a 3 by 9 matrix, I think, or a 9 by 9 matrix. I'm not sure how to do this yet, but we'll get there maybe. Okay, so the base program, the SDL GL template, uses SDL, which is used for like window creation, input handling, because all of this is platform dependent. So if you would want to write this yourself, you would need to write a different version for Windows, for Mac, and for Linux. And this is really time consuming and maybe even hard. So I used SDL here, and I will use this for the stream, like 2. And the other thing that's currently here is glad, which is to load all of the OpenGL functions, because the OpenGL functions are not like OpenGL is very old, and the modern OpenGL functions, I don't know, it's a bit strange, but the functions are not supported everywhere, or not you can't use them by default because there are no headers. So this is why you have to use the library which loads the functions from some file, and this is glad. Glad can actually be you can actually generate the files I used in the glad library using this tool. So I use this tool to create these files in here. You just tell it like, I mean, in which language you want to do this. And the most important thing here is probably the version you want to use. In our case, I need to work with OpenGL 4.1 because macOS doesn't support OpenGL functions that are later than 4.1. So I generated this glad here library with 4.1 headers, 4.1 version. Here you can see what I used to generate this. 4.1. Yeah, you can use Metal, but that's like that's platform dependent. So if I would, I mean, I can't use it because I don't know Metal, but you could use it, and it's platform dependent. So if I would then want to run the program on Windows, for example, I couldn't do it because Metal doesn't run on Windows. So and OpenGL is like the oldest, most well supported graphics API that is cross-platform. So, and it's much easier than Vulkan, for example. I don't know yet. I haven't planned to use compute shaders, but maybe it's necessary. I saw another paper where where that might be necessary. Okay, but now I want to I want to get going. So I just so I downloaded this SDL GL template and compiled the libraries. So what I like to do is, because we are writing in C++ or C, what I like to do is create a build file, so small build files. For example, the build file for the normal executable. I didn't actually write this. This is because this file supports building for Linux and Mac at the same time. But this line here is for building on Mac, for example, and you just need to call the compiler, and then you input the file you want to compile. This is the option to build in debug mode, and then you just set the include path, for example, the glad library, the SDL library, And then what I have done here is I created like a 2-pass build. Because building libraries might take a while. What I like to do is create this build libs file, which I then run using the build libs sr, which I did a few minutes ago, I think. Let's see. Yeah, here the library files are here. So what this does is you have the source files of your library. For example, in the glad library, you have the source, and this is basically the code of the library. It's okay. This looks a bit unusual, but that's basically the source code of the library. And what I'm doing then is call the compiler on the source code of the on the yeah, I don't I'm really bad at using CMake. I don't know, every time I try to use it, I make some error and spend like 30 minutes trying to debug the error. I don't know, maybe maybe I should get comfortable with CMake, but until now I just use these files, and you will see it's actually pretty simple. So how this works is I just call the compiler on the library files, on the source files of the library. Then I specify that I just want to compile the code. So basically what this does, it doesn't create an executable or something. It just takes the source and creates binary files where the code is compiled into. On Windows, I think these are object files, and here these are probably .o files. So I get an O file for each source file that I have. And again, I compile these in debug mode. Yeah, and the necessary headers for including. And then what I do is I create another file where all of the O files are like stored into. Like this is some command to do it. I'm not really sure how it works, but it just puts all the binary files into this A file. And then what you can do, so for each library, I then have an A file. For example, here I have a glad.a file, .a file. And I'm not sure. So build libs. Compiling the SDL library is a bit more complicated. That's why I just call this configure file that ships with the SDL library. Okay, this takes really long. but I was actually sure that okay, now it worked. So I don't know what I did previously, but I just built the libraries. And so now you can see after all of this is done, I have a file for the glad library, and I have two A files for SDL. And now what I can do is, because these files now contain all of the compiled code of the libraries. So I can now just reference them in the compile step of my original when I compile the actual executable I want to build. I can just feed them into the compiler, and it will take the code, and it all works correctly. These are just flags that I need to use because of Mac. Basically, on Windows, you would have to write something like I don't know. I'm not sure. These are just libraries that you want to use in your program, and these are built-in libraries for the Mac operating system. On Windows, for example, you would have to write something like you want to use OpenGL.lib or something. But yeah, that's basically how to compile this program. And if I run so if I run this file now, it compiles the main file here. And if I run it, you can see this is the template window that I showed in my first devlog episode. Now, I think you can't hear this annoying sound, but there's a sine wave in the background. So now I want to go over shortly or briefly go over this code and explain what it does. Are you all familiar with OpenGL or no? Probably not, right? Or maybe. Okay. So if first I will remove the audio stuff because we don't need that currently. So this is the main function where the program starts. And the first thing we do is we initialize SDL. So it's like a basic library initialization. And you tell it that you want to use video. So then the library does some stuff. Because so I don't want to use Vulkan because using Vulkan requires me to write a lot of code to just get a triangle on the screen. And OpenGL still works, so I thought it's just easier to use OpenGL. But I don't have anything against Vulkan. So at first, I'm initializing SDL. Vulkan is too complicated. Yeah, I mean, it's definitely hard to get a triangle on the screen. I mean, it's like 500 or 1,000 lines of code. So after the SDL library is initialized, we set up. We want to create a window. Yeah, I mean, it's probably fun to learn, but it also takes a lot of time in my experience. I tried to create a small Vulkan program once, but it was a lot of work. Okay, so the next thing is we want to create a window. And for that, we can also just call the SDL function. And because we want to display OpenGL contents in the window, so here, this is the window that SDL creates. And then inside of this window, we want to display stuff that OpenGL does. So this is why we have to set up the window with OpenGL. And in this case, I set a few attributes to tell SDL which OpenGL version to use and so on. Okay, I didn't know that. That's interesting. Um, yeah, so we set up the window with OpenGL, and then what we need to do is we need to create an OpenGL context. Immediate mode renderer. Scene manager. I think I know what you mean. I think it will be like an immediate mode renderer. So I don't want to create anything extremely complicated. So yeah, that's why I just want to load the models, create OpenGL buffers, and then render them if needed. Yeah, so after we create a window, we need to create an OpenGL context. And an OpenGL context is basically like OpenGL. You can think of OpenGL like one giant class, which has a lot of attributes. Of course, OpenGL is a C API, but you can think of OpenGL of the OpenGL context like a big class. And every time you call an OpenGL function, you modify this context in some way, and you change some settings, for example. And this is all stored in the context, in the OpenGL context. And this is why we need to create this context. And every time we render something, we need to make sure that this context is active. I'm not sure if I need to activate this here. This is probably activated automatically. Yeah. But for example, on if you were to implement this stuff yourself, you would, I think on Windows, you would need to, you would need to call um, make current. I think you need to call like this function to enable or activate the OpenGL context on Windows, for example. But since we are using SDL, it's a lot easier. Even creating an OpenGL context is a bit of work on platforms like Windows, for example. But with SDL, it's a bit easier. And Oh, okay. SDL. Yeah, so if you are using multiple threads, for example, you might also need to worry about when your OpenGL context is active. So SDL make current. Hi, hello, K Ote. I'm happy you think this is cool. Okay, yeah, this function is here. But we are using only one thread. I will get to that in a minute. And this is why we don't need to call this function. So this function here is used to enable vsync, like your monitor has a refresh rate of like 60 hertz or something. And when you swap the buffers, you can, with this command here, you can tell the system to wait with the swapping until, or like synchronize the swapping with your monitor refresh rate, so you don't get sync tearing. For example, here you can see this. If you don't use vsync, for example, you can encounter something like this where there are two, whoops, there are two different renders displayed on your screen. For example, this might be an older version, and this might be a newer version, and yeah, so this can be avoided with vsync, and additionally, you like you don't create unnecessary frames because you just create so many that your monitor can handle it. And so after we created all of the SDL stuff, we can then go to like initialize some of the OpenGL stuff. For example, this here is the call to the glad library, where all of the OpenGL functions are loaded. And after that, we can start with OpenGL. And maybe I have a tablet. Wait a second, I want to. Okay. So I want to draw some stuff. Yeah, the glCheck function is from me. Because we are using OpenGL 4.1, we can't use the GL debug message callback. If you were to use OpenGL, like any of these versions, you would want to use this here, because every time you mess something up or call something in a wrong way, then you can get a very nice error message if you use this. But I can't use this because I am on a Mac and I can only use 4.1. And this is why I have to create these ugly checks here that basically you wrap these around your OpenGL calls, and then And then it prints out all errors that it encountered, like because of the function call. For example, here, if I would make an error in this function call here, after the function call, the glCheck is like executed, and then every error that was generated is printed. You used learn OpenGL but stopped when at the model loading part because that was too complicated, or why did you stop? Okay, so currently we have everything set up. We have the OpenGL functions, and now we need to actually do something with OpenGL. And for this, I want to draw something. So how drawing works is if this is your window, basically all you draw is triangles. And these are specified by vertices. So you find tutorial boring. Okay. Well, I hope I can make this more interesting. I don't know. What cube rendering? I'm not sure. So currently, so each triangle is defined by vertices, and a vertex is like, you can imagine this like a struct 2. The most important thing of a vertex is its position. This is not valid code, but so we know where exactly the corner position is in space. And then you can also do something like you can define a color, for example, or a texture coordinate so that you can texture the coordinate. So you just specify some values at the corners of your triangle. For example, this is what I did here. I didn't define a struct vertex, but yeah, that's basically what I have done here. So here I have 4 corners because I want to draw a rectangle. Oops. So I have 4 corners. So each of these lines is one vertex. The first part is the position, which is typically a 3D vector. So 3D vector. And then I have additionally, I have a color specified, which is, for example, can be a 3D vector too. And I don't have a texture coordinate here. So this is my, this is what my rectangle that I draw looks like. I have a position and a color. And basically, I need to tell OpenGL that I have these positions and vertices here, because currently these are only in memory on the CPU. I mean, you can think of it this way. And how you do this in OpenGL is you create buffer objects. So for example, currently all the data I have is on the CPU, like the position, color, position, color, and so on. And then you can create a vertex buffer object in OpenGL with this command here, glgen buffers, vertex buffer. And this buffer is like a buffer on the GPU. So first we need to generate this buffer, and then we can bind this buffer. And then we can tell OpenGL the data that should be in this buffer. So basically, we tell it the size that we want to send it in, that we want to send into the buffer. So here's the buffer. Oh, okay. What do you mean you don't understand it intuitively? So here is the vertex buffer object, and then with this command here, we basically load everything of this CPU buffer into the GPU buffer. And then to draw everything, we use shaders. So there are vertex shaders and fragment shader. Hi, Nikita Ermolenko. Thank you. Yeah, I don't know. It's I've done this a few times and I forget the stuff too. But yeah, it helps to sometimes create a simple program to refresh the memory. So basically, oops, the vertex shader. So currently we only have data in these buffers, and to draw everything we need shaders. So what shaders do, for example, the vertex shader takes each vertex as an input and modifies it. So for example, what the vertex shader could do is it could scale the vertices, like stretch everything. So the output would then look like this. So the vertex shader basically just modifies vertices. And then to draw everything, there is an intermediate step where each, so currently it's just a stream of vertices, and depending on how you draw your object, you then take these vertices and you make triangles out of them. And this is the rasterizer. And what this thing does is it maps the triangles and creates small pixels. And each of these triangle pixels are then fed into the fragment shader, where you can shade them individually. Exactly. Yeah, the triangles, for example, are called primitives. So there are multiple primitives you can use. OpenGL. You can, for example, you can draw triangles, you can draw lines, or you can also draw points. But the most used thing is probably triangles. Web development is boring. Is that what you're saying? So the fragment shader just handles small pixels, and it's called fragment shader because the pixels are like, you don't shade pixels, but you shade the fragments of each of the triangles. So I can explain what this does here. It's not really super readable because it's in a string. Maybe I can just actually create these shaders in a more readable form. Oops. Okay. When you make a draw call. Yeah, so yeah, I will get to the draw call. I think C++ is, yeah, I mean, maybe C++ is too, yeah, too low level, probably. All right, so we have our data in the vertex buffer object, and for each fragment, for each vertex, we call this vertex shader here, and we have a position and a color. And what I'm doing here is I just tell OpenGL that the position where the vertex is, like the vertex here, is exactly where it originally was. So this is the input, and then I add an offset that I can choose with my mouse. And so this is done with uniform variables, but let me get to the let me talk to the shaders quickly. So I just tell where the position of the vertex is, and what you can do in vertex shaders is you can specify outputs, and these are, for example, if you would have some color here, like in this case, I have specified yellow here and red here. Whoa. And when I specify this as an output variable in the fragment shader, I accept these values, and then they get interpolated to each fragment. So this is why this is so a smooth interpolation of the colors. Yeah. So the outputs of the vertex shader are the inputs of the fragment shader. And yeah, in the fragment shader, you just need to tell what color the fragment should be. So in this case, I just use the interpolated edge color. And because OpenGL doesn't really know, it expects some variables here in the fragment shader, but it doesn't really know where the values are, because this is just a binary, I mean, it's a float buffer. So you need to tell OpenGL which, like the structure of your vertices. And this is what you can do with these functions. So you basically tell for each input of your vertex shader, you call this function here and tell it what the data represents. So the first location here that I have specified should be a position, and that's 3 floats. And the total size of our vertex is, in this case, 6 floats. So 6 times the size of a float. And the position starts exactly in the, like exactly at 0. So this is why here is a 0. And the second attribute is the color. So this is why we have here a 1 for the second attribute, or like the first. In this case, not the 0th. And again, it's 3 float values, and the size of our vertex is still this. And the offset is now we need to skip the position, so we just tell it that it should advance 3 floats before it can get to the color. And then we need to enable these attributes, and then we set up the buffer. So we told OpenGL what the buffer looks like, and what the buffer looks like this information here, this is stored in a vertex array object. So you have the vertex buffer object where the data is stored, and then you have the vertex array object where the information how the data looks like is stored. Could you make the vertex layout literally a struct? Yes, that's possible. But the problem is I don't have a vector struct currently. I want to create this. I mean, maybe I could even create this now. That's a good point. So basically my idea was to use the Eigen library as a vector base, so as a math library basis. And I think but if you have a struct only of floats, can it be defined at the shader the same way? Yes. It doesn't matter what your layout really is here, or like which structs you used, because when you pass this, the only thing that OpenGL sees is a pointer, like it just sees a bunch of floats. And this is why you need to call these functions to tell it what these floats mean. I want to add this as a submodule. So how can you do this again? Okay, git submodule add, and then oop. So they store their code on the GitLab servers. Git submodules. Oops. It takes quite a while, but now we have this additional Eigen folder. And to integrate this, the cool thing about this library, I mean, it has some disadvantages too, but it's a header only library. So basically we don't need to compile anything as a library. The only thing we need to do is we need to include some files into our project. And this is the file where all the header files are in. So we just need to include this in the build file. So I can add an additional include path here using the -i, and then I can just write Eigen, because this is the folder here, and that should be everything. Yeah, so the reason I wanted to use Eigen instead of GLM is because I think the library is a bit hard to read. I think it's in my opinion it's a bit difficult to read this library, like the documentation, or like generally how it's structured. But the thing about Eigen is that you have things like where you can solve a large system of equations, and I don't think this is possible with GLM. And when we implement something, I maybe just for debugging stuff or just to see how or if something works, I wanted to use Eigen because it seems to be a bit more powerful than GLM. Okay, so but GLM is a C++ library, so I need to rename this. Okay, so I just renamed the CPP file. I renamed the C file to a CPP file. I don't think, I'm not sure if this actually matters, but because we now include Eigen, we want to compile C++ code. And I think, main.cpp, and when we are compiling C++ code, we need to use the Clang++ compiler, and I think Eigen is only supported with C++ 17. Yeah, so we need to, I think it was minus std C++ 17. Oh, maybe not. And ist gleich. Okay, thanks. Yeah, it makes sense. It's equals. Did I say ist gleich? Thank you. Is that the same one you used in the physics? So the physics simulation currently in my devlog, it's not really anything complicated. I don't need to solve large system of equations. The code in my devlog series I wrote myself. But if you were to maybe use something like a conjugate gradient solver or something, you might want to use Eigen. I'm not sure. Okay, so now this should compile. Audio device. Wrong file. Yep, it still works. And now we can use Eigen for this, like you suggested. They have a struct called vector3f. Okay. That's interesting. I think it has, so in my opinion, it sometimes has a bit of a weird syntax, like how you write things, but that's my personal style. But it's definitely pretty powerful, yeah. So now I defined the vertex object here, vertex struct, like here. And I can redefine mesh data to be constructed of vertices. And I'm not sure if I can just use these initializers here. Let's see. Okay, this is pretty... I hope this works. Okay, so I have no idea. This might actually work. Yes. Okay. So now we defined the, like you suggested, the vertex struct here, because this means it's like commenting code out. So now this is our vertex struct, and we have a 3D vector for the position, a 3D vector for the color, and yeah. So now these function calls are used to describe the buffer for OpenGL, and now to draw all of this, we basically start a loop, and I will get to the creation of the shaders, but essentially we just need to bind the vertex array, which we created here. So the vertex array stores the vertex buffer that we used. So we created this vertex buffer, and we described how it looks, what it looks like. And so this is all stored in the vertex array object. And when we bind this, basically OpenGL knows all of this, like how our vertex struct looks like. And then we can just use the draw command. And in this case, I'm drawing a triangle strip, but I can also just draw triangles. The only difference here is the triangle strip makes it easier to draw a single quad here. If I just draw triangles, I need to specify 6 vertices, because I need to specify these 3 vertices for the first triangle and these vertices for the second triangle. So I would need to duplicate some of these vertices. I'm not sure actually which of these I would need to duplicate. So this is top right, top left. Okay, so I think top, this is bottom right. Oops, that didn't work. GL triangles, I think it's plural. Yeah. So now it still works. So now I'm drawing 2 triangles. And the 6 here is the number of triangles the number of vertices I'm drawing. So if I change this to 3, only the first triangle gets drawn. Okay, so I mean, there's not really much more in this program. You need to compile the shaders. That's a bit of code, but it's just you need to specify the buffer, like the string buffer of your vertex and fragment shader code. And then you call some OpenGL functions here. GL, like here GL shader source, you tell OpenGL your, like, the data of the shader. And then you compile the shader, and then you have 2 shaders, like the vertex and the fragment shader. And then you create a program, is what it's called. And then you attach these, the vertex and the fragment shader, and then you link the program. It's a bit like how C++ works too, and the shaders are very C-like, in fact. So you create these vertex and fragment shaders, and these are compiled, and then you link them like a C++ program where you create multiple source files and yeah, you link them. And before you can draw anything, you need to bind this shader. So here it's called use shader, use program, and then you can use the program. And what you can do is you can define like variables in the shader. How did this? Yeah, here uniform variables that you can use independently of your buffers. So in this case, I used a model P, I called it a 2D position, where I want to offset the model, so to say, like here. And this works by just adding the 2D position to the model. And to handle inputs, you can again use SDL. So before you render each frame, you just check if any event happened. For example, like if the mouse was pressed or something. And then you take the X and Y position of your mouse. And you need to transform it, which I might get into later. Yeah. And then I update these positions, and this is why every time I click with my mouse anywhere, the position gets updated immediately. So I think this is just error checking. So I think this is everything of the template program. So the next thing I would want to do, by the way, hello Rex Overwatch. So the next thing I would want to do is I would want to rotate the model. Because what I want to do is I want to draw a 3D model and not just something in 2D. So we need to talk about rotations. And yeah, so let me draw something. Actually, if you have any questions, I'm happy to answer them. So Yeah, I will just start. So rotations, I want to start with a 2D rotation. So you probably know if you have a, okay, that's really ugly. If you have a 2D circle and you want to get a 2D position on the circle, like for example here, that is defined by an angle, alpha for example, you might know that you can get this position by just using the cosine of the angle, and for the y, the sine of the angle. This, if the radius is 1, so of the circle, so the radius is 1, then you can use this formula to create a point on the circle. And this, you can use this to create a rotation matrix. So basically, what we want to do now, we have our points here. So here's a point here and here, and we want to rotate it around the center. And let me draw this a bit differently. So here's the x-axis and here's the y-axis. And now, for example, let's say our point is, this is not the same point as this one. So let's say our point is called A and it's at 1, 1. Then the point would be here, for example. And if we want to rotate this point around the origin with an angle alpha, for example, if alpha was like 45 degrees, then the point would lie somewhere here. So this is alpha. And the way we can do this is by using a rotation matrix. And how it works is basically you create the original coordinate system you have here and just rotate it by your angle. So for example, if we had the system that would be rotated like this, that's x prime and y prime, then we can create the system using the formula from here. So basically the x-axis of the rotation matrix is cosine of alpha and sine of alpha. And the y axis is just, the y-axis should be perpendicular to x. And in 2D, you can create a perpendicular vector to another vector if you swap these two. And negate one of them. So I think in this case we want to, because so which one you negate depends, like in one case you create this vector and in one case you create this vector. And we want to create this vector. So I think we need to flip, because the y needs to be positive. I think we need to flip this here. So now we have the two vectors of our rotation matrix. And the rotation matrix now looks like this. Here is the x vector and here's the y vector. And essentially that's how you can imagine any matrix. Basically, any matrix, you can think of it like you have an x vector, you have an y vector, and you have a z vector. And this matrix here then just looks like a coordinate system in space where x is the x-axis, y is the y-axis, and z is the z-axis. So this is what you can imagine. And what this matrix does is if you multiply it with a point, if you multiply the matrix with a point, you pretend that the point is local to the coordinate system here. And when you multiply this point, you get a new point that is then transformed to the original coordinate system. So you have an original coordinate system that's like your standard coordinate system in space. And when you multiply the point with your matrix, you transform the point from its local coordinate system, like the point is local to A. And after the multiplication, the point is then defined in the global system. So P global is like A is equal to P local. So this means you can transform a point from a local coordinate system to the global coordinate system by multiplying it with the matrix that the point is defined in. Between using the XPBD way to solve constraints individually using a large matrix to solve all of them at once, what would you say are the benefits and drawbacks of each one? So I think if you would solve all of them at once, so this is not really related to what I'm doing right now, but if you would solve all of them at once, I think you would get much more accurate results. Like if you would use an actual solver, because the XPBD just uses some Gauss-Seidel solver, and it's not that accurate. Yeah, so the benefits would be you get a more accurate result, and the drawbacks are that you spend way more time solving. Okay, so basically this is really important because what we can do now, we can use this point here, 1, 1, and pretend it was defined in our in the system of our rotation matrix here. Our rotation matrix is x prime and y prime. And if we pretend this point was defined in our rotation matrix space, then the point would lie here, approximately, or maybe like one in this direction and one in this direction, like here. And like I told you, now if we multiply this point, A, I mean 1, 1, with our rotation matrix, we transform it back into the original system. So this means that we have then rotated the point by our angle alpha. I don't know if this makes sense. This is how I think about this stuff. I hope it makes sense. If it doesn't make sense, you can let me know. But basically, what I've just told you is we can define a rotation matrix with which we can rotate points like this. So here is the x vector. Here's the y vector. Here's the y component of this vector. And then so this is the x vector, and here we define the y vector. So this is then minus sine, and here is cosine alpha. And this is a rotation matrix. So here. And yeah, we can use this now. So what I like to do is I would like to use shorter types because these Eigen types are pretty long. I like to just use V3, for example. I think. Ooh. Okay. Yeah, I've seen rotation matrices and the stuff for a pretty long time too, but I don't know, in the beginning I was pretty scared. I didn't understand the stuff, but I think if you imagine it like this, I think it's actually pretty intuitive. If you imagine that a matrix just transforms a point from its local coordinate system to the global coordinate system. Yeah, it still works. So I think you can just create Eigen. Like I want to create a function. Okay, first of all, that returns a 2D rotation matrix. And you just give it the angle. And so this is what I mean. The Eigen has a somewhat of a weird convention to initialize types, for example, you use these operators, and you can cosine. I need to include the math headers, or I don't know, maybe Eigen has some. I will just try something. Or I have another idea. So first I will define two 2D vectors that are the x and y component. And let's see if this works. Okay, this works. So then I can define the rotation matrix by first inserting the x vector and then the y vector like I showed here. Oops. This seems to work. Let's check if the matrix is actually correct. Because I'm not sure if I input this like this, if this is actually the first row or the first column. I think it's the first column, but I want to check this first. Yeah, so you said it converts not necessarily to the global coordinate system. I mean, technically, yes, that's true. So it converts the vector. So this is not necessarily the global coordinate system, but this is the coordinate system that A was itself defined in. And for this simple example here, if we assume that this is the global coordinate system, then this works. But yeah, if you want to be really specific, you need to keep in mind that the matrix just transforms the point into the system that A is itself defined in. But in this example, I assumed that it was the global coordinate system. Okay, let me just check. I need to include IO stream too. Okay, so the program works. I didn't call the function. um, oh, I used the wrong matrix type. Okay, so the first vector I put into the R matrix is 1, 2, and 1, 2 is only here. So I assume the shift operator puts the column vector, puts it like column vectors, which is good because that's what we want here to do here. Yeah, I would actually agree. I had a linear algebra class too, and it's really unintuitive what they teach you. I mean, maybe it's difficult to teach an intuition if the matrices are like n-dimensional. But in our case, most matrices are like 3-dimensional or something. And I think having an intuition for this makes a lot of sense. So now we have a rotation matrix. And oops. And we return this here. So what I want to do now is I want to rotate the rectangle. I'm not sure if SDL. Whoa. SDL GL. So I want to get the delta time. So I will use this here. Or so we can use this U int 32, it's 32. And at the end of the frame, I want to update the delta time, like how long did this take? So I store the ticks again, current ticks, U int 32. Yes. Yeah, I agree. Math itself seems too cryptic at college level. And then the inverse of the global metric gets you back to whatever coordinate. Yeah, exactly. So if you have a global, like I like to use the word global here, but if you have the point in global coordinates, you can then just multiply all of this, like from the right, with the inverse of A. And then you can see that if you multiply the global position with the inverse of the matrix, this here will cancel, and you just get the local point back. So this gets the number of so this is milliseconds. So if I subtract these, I get the past the time in milliseconds. So I want to get this in seconds, so I divide this by 1000, I think. And then delta time is equal to this. And then I need to update the last ticks. And if I print the delta time now, hopefully I get 1/60th of a second. Yeah. But it's not really, wait, is there a more accurate version? because I'm not sure. Milliseconds is not really accurate. Um, okay. So there is a more accurate version in terms of the capacity, but it still returns milliseconds. But yeah, we will just stick with this. So what I want to do now is I want to define an angle, which is at 0 at first, and then I just update the angle. And now I want to create a 2D rotation matrix here. Using the angle. And now I want to pass this into the shader. And the problem is I still have the shaders here. So maybe I want to read the shaders from disk. Let's see. Fopen, I forgot the... I'm just using this right now because I think it's a bit faster than using the SDL stuff. I mean, faster in terms of me implementing it. Probably not faster. So I want to create a function that loads a file from disk and returns the contents of it. So at first I open the file using this function here. And I want to just read the file, so I use the R operation. And then I use fread. No, I first need to get the size of the file. So you can't exactly get the size of the file, which is a bit strange, but you can use this fc command to seek a specific position in the file. For example, here the seek end. And if you do that, then you have like when you have this file object here, there is like a cursor in the file where you currently are. And you can set this cursor to the end, and then you can give you the cursor position. And that tells you the file size. Of course, now you have to set the position back to its starts, where it started, because now you want to read all of this. So first I create a buffer where all of the stuff is now stored into. And then I can finally call fread. Here. This isn't really optimal here, but it's just, I just want to quickly get the file loading from disk. And I pass in the file, and then I ignore all of the errors and just hope that it works. So I think this might work. Just to be sure, I make the buffer one step bigger and put the null terminator at the end. So this way the string, if it's written into the bytes buffer here, it's null terminated. So I can easily output it into the console. So if I now call read file, I hope this works. Yeah, okay. So basically I just read the content of the file and stored it into this bytes array. And because this is null terminated, I can just print it using printf. And now I have the context of the Vertex shader in this Vertex code here. And so now I can pass this into the Vertex and fragment shader function. So I'm going to write a function that loads a shader instead of just compiling it. And now these two are path names instead of the actual source. And then I can read both of the Vertex and fragment shader code files. So Vertex path and fragment path. And then I have Vertex code and fragment code. And of course I need to free them. This is definitely not very safe code because I ignored all of the errors. But I just hope it works. And now I can call this function here. So now I can pass this variable here like before, and instead of vertex code and fragment code, and this should work. Of course, I want to return the error of the compile shader function. Because if there's an error in the shader, I want to catch that. So now I call load shader instead of compile shader. And here I just pass the vertex shader path and the fragment shader path. I call this default.fs. So I think this might work. I'm not sure. Syntax error. Maybe this here. Okay. So now instead of using these strings here, I can delete those and I just load them from disk. So you can see these are not here anymore and it still works. Okay, so what I like about Vulkan is that you can compile the shaders and just, yeah, that's really cool. Also, I wonder how much optimization is done when I compile this here with these functions, because I assume it would take longer if this was compiled with optimization, right? I'm not sure. So now we can define, yeah, now we can edit the shaders more easily. And now I want to add a uniform variable, like the rotation matrix here. And what I can do then, so first, let me check which function I need to use. I think these are called GL uniform matrix 2F. Why? Here. Matrix 2FV, okay. So V, first I need to tell it which variable to bind to. So here we want to bind to the R variable. So I need to get the location of the R variable. And this is basically the first argument here. Then I need to tell him how many matrices I have. So because with the V argument, you can pass it multiple, but we just have one. And then we need to specify if we want to transpose the matrix. This is so transposing a matrix basically means well, transposing a matrix basically means that you mirror the matrix along the diagonal. So the transposed matrix of this here, the diagonal is the same, but because I mirrored this here, I swapped these two. So the transposed matrix is this one. And OpenGL stores the matrices in a different format. So they store it not in row major format. So how we store matrices is because in memory, the matrix is just an array, a one-dimensional array. So we store each row like here, and this is row major. But OpenGL wants its matrices in column major. So how we need to store the matrix, we need to first put A in here, then we need to put C, and then B, and then D. And as you can see, you can achieve this by just transposing the matrix. So we store our matrices like this, but OpenGL wants to store them like this. And we can convert these two formats in the, by just transposing it. Yeah, so this is why we put GL true here, because we want to convert our row major matrix to the OpenGL column major matrix. So we transpose this. So we say yes, we want to transpose it, and then we can pass the values. And this is maybe the hard part about this, because I don't know how to access elements in Eigen matrices. Is there not an easier way to do this? Why do I have to? Wait, let me try something. Okay, so this. And what about this? Okay, this works. So I assume we can get the first element of the matrix by using this command here. I hope. I'm not actually sure if this works. Because if this just returns a copy of the value. Yeah, I think this is the equivalent to the pointer value, right? Or what is this? I have no clue. I will just try this. Okay, this works. I hope it does what I wanted to do. So now let's just put the identity matrix in here. And check if nothing breaks. So what is this? This looks like the identity matrix. Okay. So now we want to get the XY position of the position we put in, and we want to rotate this with the rotation matrix. And hopefully this should change nothing. As you can see, the quad still looks the same. And now if I change this so that I put the actual rotation matrix in here, it rotates, but it looks really strange. I think this is because the viewport is not a square. So I think this still works correctly. But I also think this should rotate in the other direction. Because it rotates clockwise, and I think it should rotate counterclockwise. So I'm not exactly sure why that is. Yep. I didn't set up the viewport transformation, but this is for a later step. Um, does anyone have an idea why it rotates in the other direction? Um, so I am not sure. Wait, maybe. Let me check something. Wait, that's a stupid test. Wait. Okay, this looks pretty cool. But I was actually just interested in... So the data array is stored... Okay, so I thought Eigen stores its matrices like this, but actually Eigen stores its matrices exactly like OpenGL does, because you can see this is the matrix. We have the first vector is 1, 2, and the second vector is 3, 4. And how I stored my matrices in the game, in my devlog, was I stored this thing first, then this, then this, then this, which is row major, like I tried to explain here. But Eigen stores its values in column major form, like here. So we don't actually need to transpose this. And if I do this now, it will rotate in the correct direction. Okay, nice. Okay, the last thing because I already streamed 2 hours, the last thing I want to do is just make this in 3D, or like a 3D rotation of the plane. And the way this works, instead of only looking at x and y, only looking at an x and y coordinate system, we now have 3 dimensions. And we define rotation matrices for each of these axes. So for example, if we want to define a rotation matrix that rotates everything around the x-axis, we can do that by looking at the system from the direction of the x-axis and whoa. So currently we look at the system from this direction, and to make it appear like this coordinate system, we just for our mental image, we rotate this like here. And then we have the y and the z vectors. And now we can, in a similar fashion, we can just define the rotation matrix. So the x vector is unchanged. So you can actually look these up. Here. Like here. This is what it looks like. So basically, the x vector is unchanged because we rotate everything around the x vector. So the x vector itself doesn't change. And we don't want to change the y and z coordinate of the x components of the y and z vectors. So now we have just this 2x2 part here left, and we can just treat the system in the 2D case, like here. So we can use cosine of alpha and minus sine of alpha, sine of alpha, and cosine of alpha, just like it's defined here. And in a similar way, we can define all of this for the other coordinate spaces. So this is for a rotation around the x-axis. To get the same thing for the y-axis, we now need to look from the at the system from the y direction. And in this case, the system looks like this. Well, yeah, the system looks like this, and we are looking at this from the y direction. So the matrix, again, the y-axis is the same, and we don't want to change the y components of the x and y and the x and z vectors. So now we can treat this again like a 2D case, but in this case, because our system is flipped, like in the original case, the y-axis points up, but here it points down. So this would rotate in this direction. To make it rotate in this direction, we basically flip two of the coordinates, like you can see here. So instead of just defining cosine of alpha, so instead of making this negative, which would rotate everything in this direction, we make this negative. So now it still rotates in this direction. And the last thing is the z. In this case, we look at this from the z direction. And this is basically like the original case. We have our x direction, and we have the y direction. And again, we don't want to change the z vectors and the z components of the vectors. So we can just insert this here. So this is how we can rotate around the default coordinate vectors. So let's define these functions quickly. First, I create the rotation for x. And instead of 2D vectors, I now need to define this with 3D vectors. So the x, y, and z vectors here. The x vector is just one. It's just the x vector in this case. And the other two are like the cosine and the sine, like you can see here. And the z vector is the minus the sine and the cosine. And then again, we can push all of these vectors into the matrix and return it. So now the other functions for the y and the z. Here we want to have the x vector with the cosine and the sine minus the sine. The y vector should just be the y vector. And the z vector with the sine and the cosine. And lastly, the z rotation Okay. So now we have all of these functions, and if I would replace because currently all we are doing is we have this cube here. It's a bit large. And this is where our rectangle gets drawn in. So here actually this gets drawn here in the middle of the cube. So this is what OpenGL wants us to draw in. Basically, we should draw everything into a cube with side lengths 2, where here in the middle of the cube is the origin 0, 0, 0. And so each of these corners here is like a position. For example, this here is -1 because it is 1 in this direction, in the negative x direction, then +1 in the y direction, and in the z direction it is, I'm not actually sure if this is 1 or 0. 1 or -1. But it's either 1 or -1. I'm not sure. So our rectangle gets drawn in the middle of this cube here. So what we can do is we can use a Z rotation instead of a 2D rotation, and this should still work. This should still rotate our rectangle. And of course, now we need to pass a 3 by 3 matrix. So we need to change this in the shader. And I hope this still works. Yep. So here it works exactly like before. So the last thing I want to do here now is I want to just make our rectangle rotatable with the mouse. So in this case, we need some mouse move event from SDL. I'm not sure what it's exactly called. Let's see. So I think we can just call mouse motion here. Yep, and every time I move my mouse, I get this event here. And I can use this event struct here then to access the coordinates. So basically I have event dot, and then I need to access the motion struct here. Which is called just motion. So this event struct is like a huge struct that contains all of these events at the same time, like in a union. And I think I can then access these by just calling motion and then x, for example. And every time I move the mouse, I get the x position of the mouse. So I want to store these now. So each time the mouse moves, I just set these. And at the same time, I want to store the last position of the mouse. So then I can get a delta of the mouse, delta position. And I don't want to do this in here, because if I do this and the event gets called multiple times, I lose some mouse motion. So essentially, I want to do this here. Last mouse X is mouse X, and last mouse Y is last mouse Y. So these contain the mouse positions, and after the event, the mouse position might get updated. And then I can compute the mouse delta here. And if I run this now, motion. I should get the relative X motion. Yep. So when I move my mouse now, I just get how much I moved my mouse in the console. And with that, I can now define like, okay. So what I want to do now, I want to rotate this rectangle here. When I move my mouse in this direction, I want the rectangle to rotate around the y-axis. So x motion or delta x, y rotation. And when I move my mouse up or down, I want the object to be rotated around the x-axis. So delta y is x rotation. Wait, really? This here? I'm not sure what this is. Relative motion. It might be the relative motion, but I'm not sure. Okay, but it works now. So here, now I want to store an angle for the y and the x rotation. And for the y rotation. And I want to increase these with the delta. So like here, when I angle x, I want to increase this with the delta mouse y. And I probably need to scale this. And the same one with the Y angle. So if I move my mouse in X direction, I want to change the Y angle. And now we can construct here two matrices. So first, let's just rotate our rectangle around the x-axis. And if we do that, nothing actually happens. Great. Oh, I wanted to use this one. So as you can see, it rotates around the x-axis now. And if I make this dependent on the actual mouse angle, I can, okay, I need to remove the feature that I can, wait. So like this, and I only want to, update the angles when I press the mouse button. So I want to this button down like 0. And for simplicity, I will just take any mouse button. So I only want to move the angles if I press the mouse button. Oops. And now you can see when I drag my mouse, maybe I can even make this a bit stronger. I can rotate the triangle around the x direction. And additionally, we can now append a y rotation by just multiplying. So multiplying two matrices. So first, this matrix is executed, and then this here. Okay. I mean, I can rotate this now, but it's a bit slow. And I think it might be better to first rotate around the y direction. Well, so the rotation is not really intuitive, but you can see it somewhat works. And yeah. So I think I would leave it at that for now. Yeah, perspective projection probably. But that would take a bit too long to do it right now, so yeah, probably. Okay, so I think I would continue in another stream or in the future. I will upload this on my GitHub if you want to try it out or something. So right now I'm at the end. For those of you who are still here, maybe you can tell me or let me know some feedback if you thought this was interesting or if it was really boring. And you can be honest. It might, I don't know. I feel like it was a bit boring. But it isn't necessarily the most interesting thing, starting with OpenGL. I think this might get more interesting in the future. Okay. Hello, Unobot. I'm glad to hear that. Okay, yeah, then if you have no further questions, I would end the stream. Thank you for watching. Thank you. We sent. Glad to hear that. Okay. Bye.